Welcome back, everybody. In this video, we'll be finishing up section 8.1. And so in this first part, we'll be looking at the different test statistics that you'll use in conducting a hypothesis test. Depending on what it is that you're trying to test, you'll use a different test statistic. Proportions, you're using a normal distribution, and the test statistic is p hat minus p over the square root of pq over n, where the p is the hypothesized value from the null hypothesis. For the mean, there were two different distributions depending on whether or not we knew sigma. If you know sigma, you're going to use the z. If you don't know sigma, you're going to use s and in place of sigma, and so you'll be using the t distribution. For tests of the standard deviation of variance, we'll be using the chi-squared distribution, and its test statistic is shown here to the right. There's three different types of hypothesis tests depending on the structure of the alternative hypothesis. If the alternative hypothesis is a not equal to, then that is a two-tailed test. If the alternative hypothesis is a less than, it will be a left-tailed test. If the alternative hypothesis is an greater than, then it will be a right-tailed test. So what's shown in pink here in our illustrations is the rejection region, also called the critical region. There are two of them in the two-tailed test, and then it's either left or right, depending on whether you have less than or greater than in your alternative hypothesis. So there's two different ways of finishing the hypothesis test. There's what's called a critical value or traditional method, and then there's also a p-value method. We're going to look at both. First of all, the critical value method. So basically, you begin by finding the critical values which separate the critical region, where we reject the null hypothesis, from the values of the test statistic that don't lead to rejection. So in this case, you begin with the alpha, and you put that into your picture. So you draw a picture of the distribution, normal distribution, t distribution, or chi-squared. And then depending on the type of hypothesis you have, is it left, right, or two-tailed, you would draw your alpha in either the left, right, or split it into two parts and put it into each of the each half into the two tails. And then, so what you're doing is, let's say that alpha is 0.05. Okay, and so what you would do is you would put, for the left-tailed test, you would find an area of 0.05 in the left tail. What would be the critical value for that, either z or t or chi-squared? For a right tail, we would need 0.05 in the right tail, so 0.95 to the left. Again, we want to find the critical value for that. For 0.05, if we had a two-tailed test, 0.05 divided by 2 is 0.025, and so we would have 0.025 in each tail. Okay, so the critical region is what's shown in yellow here, also called the rejection region, is the area corresponding to all values of the test statistic that causes to reject the null hypothesis. So you'll, in the critical value method, you will start with the alpha, draw a little sketch of what the distribution looks like, then figure out the area, and then from the area, determine what that critical value is going to be. Then you'll calculate the test statistic, depending on what it is that you're trying to test. And then if the test statistic comes out in the rejection region, then you would reject the null hypothesis. So if for a left-tailed test, if the critical value, or if the test statistic was less than our critical value, we'll reject the null hypothesis. If the critical value is higher than, right, if the test statistic is higher than the critical value in the right-tailed test, then we would reject. If the test statistic came out in either of the two tails for the two-tailed test, then we would reject the null hypothesis. In any case, for the critical value method, we start with the alpha. We put the alpha onto our picture. From there, get a critical value, calculate a test statistic, and compare it to the critical value. The second method, called the p-value or probability value method, the big difference between this and the critical value method is that this one is going to end with alpha, okay? So rather than starting with alpha. So what we'll do is we find the p-value, which is the probability of getting a value of the test statistic that is at least as extreme as the one from the sample data, assuming the null hypothesis is true. So for this one, you will still draw a picture of the distribution, but instead of putting the cutoffs for the left, right, or two tails, instead of that coming from the alpha, those will be from your test statistic. So you'll calculate the test statistic first, you'll put that onto the distribution, okay, and then calculate the corresponding area. If it's a left tail test, the p-value is the area to the left of the test statistic. If the critical region is in the right tail, the p-value is the area to the right of the test statistic. If the critical region is in two tails, that is, it's two-tailed test, then the p-value is twice the area in the tail beyond the test statistic. So for the two-tail one, you have to multiply by 2. So there's a flow chart kind of that governs what to do here. This will be easiest to follow in the course of an example, but just to give it a quick run through, we start, decide what kind of test we're doing. Is it left-tailed, right-tailed, or two-tailed? If it's left-tailed, the p-value is the area to the left of the test statistic. If it is right-tailed, the p-value is the area to the right of the test statistic. If it's two-tailed, then we have to decide, is the test statistic on the negative side or left side of center, or is it on the right side of the center? If it's on the left side of the center, then it's the area to the left times 2. If it is the area, if it's to the right of the center, then the p-value is twice that area to the right of the test statistic. Okay, once you've done all of that, then time is to make a decision. For the p-value method, if the p-value is less than or equal to alpha, you reject the null hypothesis. If the p-value is greater than alpha, you fail to reject the null hypothesis. And what that means is the p-value is derived from our sample data and is basically the probability of us getting a sample like we did, given that the null hypothesis is true. If it says that the null hypothesis, if it says that the probability is really small, the probability of us getting a sample like we did, if that probability is really small, then you know what? Probably the null hypothesis is not true. If the p-value is higher than our alpha, then that isn't conclusive evidence or convincing evidence that the null hypothesis is not true, and so we would fail to reject that null hypothesis. The critical value method, if we calculate the test statistic, is it in the tail? Whichever tail we're talking about. Is the test statistic in that critical region, what I was drawing as yellow before? If it is, then you'd reject the null hypothesis. If the test statistic doesn't fall in that critical region, then don't reject the null hypothesis. Once you've decided whether or not you're going to reject the null hypothesis, then we have to come up with the wording for the conclusion. The outcome will always be, regardless of whether you're using critical value or p-value method, it's always going to either be that you fail to reject the null hypothesis or that you reject the null hypothesis. Note that failing to reject the null hypothesis is not the same as proving the null hypothesis is true. We're never going to prove the null hypothesis is true. We always assume the null hypothesis is true, and our sample data may either support the alternative, or it won't support the alternative, but it will never support the null hypothesis. Okay, depending on how our original claim is written, that will determine for us how we're going to write the conclusion. So depending on whether the claim, what it is that we're trying to establish, if it's in the alternative hypothesis or in the null hypothesis, that's going to help dictate the wording of our conclusion. If the original claim does not include equality and you end up rejecting null hypothesis, okay, if you're rejecting the null hypothesis and the claim is the alternative, then that means that there is sufficient evidence to support the claim, which is in the alternative hypothesis. Okay. If the original claim is in the null hypothesis and you don't reject it, there's not sufficient evidence to support the original claim. If the original claim includes equality, so it's in null hypothesis, and you reject it, then there's sufficient evidence to warrant rejection of that original claim. And then finally, if the original claim is in the null hypothesis and you fail to reject it, then you'd say there's not sufficient evidence to warrant rejection of whatever that original claim is. So it takes a little time and practice to get used to the wording of that. You just need to think about which hypothesis your claim is in. If it's something that you're trying to support, hopefully you set it up so that the claim is in the alternative hypothesis, but you need to decide which hypothesis contains your claim, and then which way did your hypothesis test come out? Did you come out rejecting that null hypothesis, or did you fail to reject it? And then you just word it in kind of everyday language. Okay, make sure, by the way, when you write out that conclusion, it should be in everyday terms. And should address the original claim. You shouldn't include technical terms like reject the null hypothesis. Remember that the result of your analysis should be digestible for people who don't have training in statistics. And so you should put it in terms of whatever the study was about in the first place. All right, so that takes us up to the end of this part. Let me know if you have any questions, and have a great day.